Hello guys, I hope this video finds you well. Today I wanted to discuss the common mathematical question that which is what is 0 raised to the power 0. So you kind of encounter this a lot when you're working with limits. When you start working with limits, it's like 0 is always an annoying number to deal with, right? So we are going to face the dilemma and answer why the value of 0 raised to the power 0 is what it is. So to begin with, let's learn why 0 raised to any other power, for example 0 raised to the power 1, 0 raised to the power 2, or 0 raised to the power minus negative numbers. Wait, negative numbers actually like become undefined because then you will get 0 in the denominator, which is simply undefined. Like 0 raised to the power minus 3 is just 1 upon 0 raised to the power 3, which is infinity, undefined, whatever you want to call it, right? So 0 raised to any positive number is simply equals to 0. Why is that? For example, 0 raised to infinity even is 0, because you are simply multiplying zeros with themselves. You are multiplying 0 multiplied by 0 multiplied by 0 multiplied by 0 and so on, right? So it's just basically equal to 0. Anything multiplied by 0 multiplied by 0 is equals to 0. I do not know why this tool never works in Notepad. The Notepad sucks about this. It's just really bad here. Yeah, the selecting always works in Notepad for some reason. Okay, so to start with, we are going to solve and prove why any other number raised to the power 0 is actually 0. Okay. Yeah, this is a voiceover. You you might have realized I forgot what I did after this. So yeah, I was talking about why 0 0 is equals to 1. Like you're like, okay, why is 0 0 equals to 1? That makes no sense. Any other power of 0 is either undefined or 0, but like when you raise 0 to the power of 0, you get a 1. Why is that? Even desmosis or desmosis is defined at 0. 0 0 is 1. Desmos is it is equal to 1, not undefined at 1. So to begin with, here I hope I am right. I wanted to discuss why any other number that is not 0 raised to the power 0 is equals to 1. So you have any real number a, any real number, how big, how small, doesn't matter. You have a raised to the power n and a raised to the power m. A raised to the power n divided by a raised to the power n, right? N and m are powers of a. So basic indices tell you that the expression is equal to a raised to the power n minus m, right? Where n, like if you analyze an expression where n is equal to m, you will get a raised to the power n minus n, which is equals to a raised to the power 0. N minus n equals to 0, right? So if you have any expression where the numerator matches the denominator, the expression equates to 1, right? A square upon a square equals to 1. So a n upon a m, which is equal to a n upon a n, is going to be equal to 1, right? So a n upon a n is 1. So a raised to the power 0 is 1, right? So that's the basic proof for the first part. The second part is the second limit goes to what does limit x raised to the power x approach when x approaches 0, right? This is the second point which I am going to discuss. Limit x is approaching 0 where the expression is x raised to the power x, right? So to deal with this, we are going to pull a common mathematical tool which we do, which is introducing exponents, which is using the Euler's number, which we do. What we do is put the expression, the whole expression, into natural log, which is a power that Euler's number is raised to. If you think about it, this expression is effectively equal to the initial expression, because ln x raised to the power x is basically saying what power of Euler's number you need to raise to get the expression x raised to the power x. So, and you are just raising Euler's number to that exact power, so you're just getting back to x raised to the x, right? So this is a good tool you become used to when you do solve a lot of limits with indices. Honestly, it's like very commonly used nowadays. Very commonly used in college level maths. Okay, so yeah, um, limit x approaching 0 where, yeah, so the common natural log power rule, where you put the power outside the natural log and the expression stays inside. Yeah, so if you look at this expression, the power you become it like kind of gives an intuition why the why the value is going to be equal to 1, right? Because natural log of 0, when you are approaching 0 from the right hand side, from the positive x-axis side, natural log of 0 is simply equals to minus infinity, right? Yeah, so I wrote the limit just to clear any misconceptions. uh, yeah, minus infinity, and 0 multiplied by minus infinity is basically just 0, right? Anything multiplied by 0 is 0, so you get the idea why e raised to the power x ln x is equals to e raised to the power 0. But let's just solve the limit now. This is a common identity of limit that I applied. The expression is actually in the power of the Euler's constant, right? So just put the limit there as well. So we need the expression in a form that is adequate so that we can apply L'Hopital's rule, the L'Hopital's form, I guess if they call it. The L'Hopital forms, the requirement for L'Hopital's rule is two types of undefined expressions, which is 0 upon 0 or infinity upon infinity, right? That is because like when you reach these values, it's the rate of change that really determines the value of the expression, right? Yeah. So limit, yeah, I'm just gonna consider the power here. I start the actual expression before like continuing so that you don't get lost and I don't get lost. So this is a common thing mathematicians do to get expressions in L'Hopital's forms, right? A form which in which they can apply L'Hopital's law, because 1 upon x as x is approaching 0 just approaches positive infinity, and ln x as x approaches 0 from the right hand side is, we are considering the right hand side, by the way. I forgot to mention the positive here. I'm really sorry about that. Which is just 1 upon 0, so that is just infinity upon infinity, right? Which is undefined simply. So you get the form which in which you can apply L'Hopital's rule now. That is really good, right? So you would find the derivative of the numerator and the derivative of the denominator and then apply the limit. The derivative of ln x is 1 upon x. Pretty simple. 1 upon x has a derivative minus 1 upon x square. The square and x cancel out. The x goes into the numerator. The negative remains. You get limit x approaches 0 minus x. You cannot associate a negative sign with 0. So x is just approaching 0. You will get straight 0, right? So yeah, you'll just get 0. So back to the actual expression, we get e raised to the power 0 because the limit is approaching 0. So any number like we studied earlier is equals to 1 when you raise it to 0, including Euler's constant, right? So that was a small proof for our expression why 0 raised to the power 0 is 1. But like if you look at okay, so in Desmos, when you put the expression x raised to the power x and like graph it, Desmos says that your value is actually like the expression is actually defined at x equals to 0. It is defined, it's like a solid dot there. An empty dot means that the expressions are undefined. But any other expression like this fraction here is just undefined. The Desmos says it's undefined because the denominator becomes 0, right? This leads to a kind of a paradox here. The paradox where you need to know the basic rules of mathematics. The basic rule is you cannot divide by 0 at all. Like dividing by 0 is just stupidity or nonsense, right? That is basically the rule of mathematics that solves this paradox. You cannot like put a 0 in the denominator deliberately, right? That is because it will just get undefined there. Why it is a paradox is because like, as we studied earlier, a raised to the power 0 equals 1, right? So if we say a is equals to 1, if we say a is equals to 1 and we apply the same thing we did there, the derivation for why a raised to the power 0 is equals to 1. So 0 upon 0, 0 raised to the power 1 upon 0 raised to the power 1 should be equals to 0 raised to the power 0, which is equals to 1, right? So, and we all know 0 raised to the power 1 and 0 raised to the power 20 are equal because both are zeros, right? So you can write 0 raised to the power 1 upon 0 raised to the power 20, which is going to be equal to 0 raised to the power minus 19. 0 raised to the power minus 19. Hear me out. 0 raised to the power minus 19, which is going to be equal to 1. Like, what? Why is that? We are not getting the 0 raised to the power 0 expression here. So why is that? Why is this happening, right? The paradox is saved by this mathematical law that you cannot deliberately divide by 0. The graph actually in fact is undefined at x equals to 0, and Desmos just uses the common mathematical notation that almost everybody has adopted to using because 0 is about 0 is useful in some applications. So the limit is actually just for approaching closer and closer to 0. The limit has nothing to do with x equals to 0, which is with which is just the case with every other limit, right? But it is actually undefined. It is an intermediate form. It is an intermediate form. When you are approaching 0 in an expression x raised to the power x, right? It is an intermediate form, but Desmos doesn't because like the mathematical notation have adopted to the fact that you can just make use of 0 raised to the power 0 equals to 1, right? It helps to like just say that. Mm-hmm. So, like an example would be using combinations. This is a funny example. Bear with me, I guess. The funny example is that you are going to pick nothing. You are going to pick nothing from a set of nothing, right? From nothing, you want to pick nothing. That is the example. You have you have a bunch of nothing, like you have an empty box and you want to pick nothing from it. You want to take out an empty hand from it. In how many ways can you do that? In how many ways can you pick nothing out of nothing? It's funny, I swear to god. Like it's real, it's real, trust me. So so just to do this, like, in how many ways can you pick nothing out of nothing? Tell me, how many ways can you pick nothing out of nothing? I don't have any example for that either. So that there is only one way you can pick nothing out of nothing, which is just picking nothing. You can just decide to choose nothing, and that is one way. That is one abstract way, right? So that is an example where 0 to the power 0 is useful, right? It's like you do this so that in programming you don't have to set out other conditions, so like not encounter a runtime error or something like that. This is generally helpful sometimes, but it's still an intermediate form. It is still an intermediate form. Yeah, that was a misconception that I wanted to clear. um, yeah, that is pretty much it. Desmos is also used to the notation here. Desmos also uses the same notation here. Yeah, the Desmos is basically programmed the same way, like I said. Okay, so we are done now, and yeah, thank you for watching. I hope you come back for more. Bye bye.